Let's unlock the visual secrets of piecewise functions, where different rules apply to different parts of the graph. First, we need to understand what a piecewise function is. It's like a function that's split into multiple pieces, and each piece is defined by its own equation over a specific interval. Think of it as several distinct functions sharing the same graph space, but only showing up where they're told to. Our first crucial step is to identify the boundaries for each piece. These are the x values where one function's rule ends and another's begins. We'll often represent these as inequalities, like x is less than 2 or x is greater than or equal to 2. These boundaries are critical. They're the points where the graph might change direction or have a visible break. Now, let's take the first piece. We'll focus on its equation and its assigned interval. For example, if we have the function y equals 2x plus 1 for x3, we'll treat y equals 2x plus 1 as a regular line, but we'll only draw it for x values strictly less than 3. To graph this first piece, we'll find a couple of points within its interval since the inequality is less than 3. We know our graph will stop before x equals 3 at x equals 3. We'll mark an open circle to show that this point isn't included in this piece. Then, we'll draw the line connecting our points up to that open circle. Next, we move to the second piece. Let's say our second function is y equals x plus 5 for x a circumflex, yen 3, we'll graph y equals x plus 5, but only for x values greater than or equal to 3. For this second piece, we'll again find a couple of points since our interval is greater than or equal to 3. The point at x equals 3 is included, so we'll place a solid dot at x equals 3 on this line segment, and then draw the line extending from that solid dot to the right. And there you have it. By graphing each piece according to its specific interval and paying close attention to those open and closed circles at the boundaries, you've successfully visualized your piecewise function. This visual representation helps us understand where the function increases, decreases, or even has jumps.